in the last lecture we developed a graphical tool what is called a Smith chart by transforming the impedances onto the complex gamma plane. So, we see here the Smith chart which is superposition or constant resistance and constant reactance circles. Before we go into the use of the Smith chart for the transmission line calculations, let us develop one more set of circles what is called the constant VSWR circles, which are to be superimposed on the Smith chart for doing transmission line calculations. We know that the reflection coefficient at any point on the transmission line gamma at a distance L is equal to the load reflection coefficient gamma L e to the power minus j 2 beta L, where L is the distance from the load point, gamma L is the reflection coefficient at the load, and beta is the phase constant on transmission line. Let me remind you, we are still discussing the transmission line which are lossless transmission line, and therefore, the attenuation constant of the transmission line is 0. If we write this reflection coefficient at the load explicitly as the modulus of reflection coefficient and the phase angle, we can write this as the mod of gamma L e to the power j theta L, where theta L is the phase angle of the reflection coefficient at the load e to the power minus j 2 beta L. So, the total phase of the deflection coefficient at a distance L from the load will be theta L minus 2 beta L. So, on the complex gamma plane, if I get the reflection coefficient, it has a magnitude whose value remains constant, but the phase changes as we move on the transmission line, and L is positive if we move towards the generator. So, as we move towards the generator, the phase becomes more and more negative. The distance of the point from the center, which is the magnitude of the reflection coefficient, that remains constant. So, essentially this represents a circle on the complex gamma plane, which is center which is same as the origin of the complex gamma plane. So, I can plot this on the complex gamma plane. This is u, this is jv, and I get a circle on the complex gamma plane whose radius is mod of gamma L and the angle is theta L minus 2 beta L. So, as we move towards the generator, L is positive. So, this quantity becomes more and more negative. So, the point essentially moves on this circle in the clockwise direction. So, the movement of on transmission line by distance L is equal to a rotation on this circle in the clockwise direction. Now, for this circle, the magnitude of reflection coefficient is same no matter what point you take on this. So, the phase angle changes for different points on transmission line, but the magnitude of reflection coefficient remains same, and we know that the VSWR on transmission line is 1 plus mod gamma L divided by 1 minus mod gamma L, that we saw last time. So, for this circle, any point on this circle, this quantity VSWR is same because mod gamma L is same for all the points on this circle, and that is the reason the VSWR is same for all points on this circle. So, you take any impedance which lies on this circle, its magnitude of reflection coefficient will be same, and that is the reason its VSWR will be same. Consequently, we call these circles as the constant VSWR circles. So, these circles we call constant VSWR circles. These circles you have to draw whenever we solve the transmission line problem using Smith chart. So, Smith chart readily gives you the set of circles which are constant resistance and constant reactance circles, and while solving the problem we have to draw the circle what is called the constant VSWR circle on the Smith chart and then do the transmission line calculations. As we can see, there are special properties for the constant VSWR circles. Firstly, the center of all constant VSWR circle is same as the origin of the complex gamma plane. Secondly, for all passive loads, the magnitude of reflection coefficient is always less than or equal to 1. So, these circles are concentric circles with origin as the center of the circles, and the maximum radius for this circle is 1. Larger the radius gives you more reflection coefficient, that means worse is the impedance match. So, what that tells you now is that if you take a point which is closer to the origin of the reflection coefficient plane, it denotes smaller magnitude of reflection coefficient, that means smaller reflection, that means better match. So, visually whenever we have a impedance marked on the Smith chart or on the complex gamma plane, visually if the point is closer towards the center of the Smith chart, better is the match, because that is representing smaller value of the magnitude of the reflection coefficient. With this understanding and superposing the constant VSWR circle on the Smith chart, then we can solve the transmission line problems. However, as I mentioned last time, you may require many times the connections of transmission lines which could be in the form of parallel connections. And we know from electrical circuit analysis that whenever we have parallel connections, it is easier to deal with the admittances rather than impedances. Up till now we have been talking about the load impedance or any impedance on transmission line. However, now if you want to make parallel connections, we have to represent these loads and other characteristics in terms of admittances. So, what we first do before we go into analysis of transmission lines using Smith chart, let us find out how the Smith chart would look like if I do all the calculation in terms of the admittances. Since the Smith chart deals with the normalized impedances, as we have seen, the same thing we can do for the admittances. So, we can first define what are called the normalized admittances on transmission line, and for that we will require what is called the characteristic admittance of transmission line. So, what we do first, we define a quantity what is called the characteristic admittance, which is denoted by Y naught, and that is nothing but 1 upon the characteristic impedance of Z naught. Then every admittance which we see on transmission line is normalized with respect to the characteristic admittance of the transmission line. So, following the same notation as we did for the impedances, the normalized admittance which is denoted by Y bar, that will be equal to the actual admittance divided by characteristic admittance on the transmission line. Similarly, the load admittance normalized will be equal to the actual load admittance divided by the characteristic admittance of the transmission line. Once we make this definition for the characteristic admittance and the admittances on the transmission line, then one can ask, how do I write down now the reflection coefficient in terms of the admittances? Going from the definition of the reflection coefficient which you have derived in terms of the impedance, the gamma at any location is Z minus Z0 divided by Z plus Z0. The admittance will be 1 upon Z, the characteristic admittance will be 1 upon Z0. So, this one we can write as 1 upon y minus 1 upon y 0 divided by 1 upon y plus 1 upon y 0. That will be equal to y 0 minus y divided by y 0 plus y. If I want to write in terms of normalized admittances, I can take y 0 common. So, that will be equal to 1 minus y bar divided by 1 plus y bar. If I take negative sign common, this will be minus y bar minus 1 divided by y bar plus 1. So, this we can write as y bar minus 1 divided by y bar plus 1, and the minus sign is nothing but a phase change of 180 degrees. So, this is same as e to the power j pi. So, a reflection coefficient, if I write in terms of admittance, normalized admittances, it is same as if I had got the reflection coefficient by using normalized impedance, except there is going to be a phase change of pi. What that means is, if I take the same normalized value of impedance and admittance and calculate what the reflection coefficient would be, the magnitude of reflection coefficient would be same, but the phase difference between the reflection coefficients will be 180 degrees. Or in other words, on complex gamma plane, the 180 degrees phase change would correspond to a rotation by an angle 180 degrees. So, essentially the normalized admittances and normalized impedances can be dealt in a same way, except whenever we are doing calculation for the normalized admittance, there is a rotation of 180 degrees on the complex gamma plane. Otherwise, all other things remain same. So, what essentially we are saying is, if I take the gamma plane as we did earlier here, and I take certain value of the normalized impedance, I get a reflection coefficient here. If I take the same normalized value for the admittance, the point has to rotate by 180 degrees. So, if I take a diagonally opposite point on this circle, that is the point which will correspond to the complex reflection coefficient for the normalized admittance. So, essentially as far as the set of circles are concerned, what is called the Smith chart, if I rotate every point on the Smith chart by 180 degrees, I get the set of circles for the normalized admittances. Let us say the normalized admittance is denoted by small g plus jb. So, y bar, which is normalized admittance, and let us denote that by the conductance plus the susceptance, which is jb. This is same as the actual conductance plus the actual susceptance divided by the characteristic admittance y naught. So, if I have a admittance on line which is given by the conductance G plus susceptance B and normalized characteristic admittance is y naught, I can calculate the normalized admittance on the transmission line, which is G plus JB. So, if I interchange R with G and X with B, I will get set of circles which will be constant G circles or constant conductance circles and constant susceptance circles, and these circles will be rotated version on the complex gamma plane by 180 degrees. What that means is, if I had initially a chart which looked like that, there is a rotation of every point of this around the center of the Smith chart, which is the origin of the complex gamma plane, by 180 degrees. So, if I keep the gamma plane fixed, that is this is the real axis of gamma plane, this is the imaginary axis of gamma plane, then every point on this will rotate and the constant conductance and constant susceptance circles would look like that. So, in this case now these circles which were earlier constant resistance circles, now they are the constant conductance circles. These circles which were constant reactance circles, now they are constant susceptance circles. So, nothing is changed as far as the Smith chart is concerned, except this whole Smith chart is rotated by 180 degrees. So, now there are two things. If I keep the axis for the complex reflection coefficient same, then the Smith chart will be rotated by 180 degrees. Alternatively, I can keep Smith chart same and rotate the complex gamma axis by 180 degrees whenever I do the calculation for the admittances. So, if I now develop an understanding that, well, I will not rotate the Smith chart I will use always in this form. That means the most clustered portion of the Smith chart is on my right. Then if I do the impedance calculations, the positive real axis is towards right and the positive imaginary axis is upwards. However, if I do the calculation by using this chart for admittances, then the real axis will be on my left and the imaginary axis will be downwards. Normally, whenever we do the Smith chart calculations, we do not rotate the Smith chart. We follow this convention that the Smith chart is fixed, but for impedance the gamma axis is like that, whereas when I go to the admittances I get the gamma axis which will be like this. So, depending upon whether we are doing calculation for the impedances or admittances, and if I require the phase measurement, phase angle measurement in the complex gamma plane, then appropriately the axis has to be rotated by 180 degrees depending upon whether I am using the impedance or I am using admittance. But if I do not want to find out the phase of the reflection coefficient, then the axis of gamma plane does not come into picture. It is just the impedances and admittances which we want to use on the Smith chart. So, without worrying of the complex gamma plane axis, we can use the same Smith chart for the admittance as well as for the impedance calculations. That is the reason, if you look at the Smith chart carefully, you will see that the upper half of the Smith chart is denoted by x comma b plus x comma plus b, lower is denoted by minus x comma minus b. The circles are denoted by either r or g. So, any normalized value of r which is equal to the normalized value, same normalized value g, it will represent the same circle. So, as long as we are dealing with the normalized quantities, the impedance and admittance can be treated exactly same way on the Smith chart. However, the normalized values of g and r or b and x have different meaning physically. Do they represent same physical conditions? The answer is no. For example, suppose I consider r equal to 0, x equal to 0, that corresponds to the short circuit conditions. The impedance is 0 at that point. But if I take a normalized value g equal to 0, b equal to 0, that represents the admittance equal to 0, that is not short circuit, that is the open circuit condition on the line. So, the normalized values of impedances and admittances can be treated exactly same way, but when we go for the physical conditions, the physical conditions are not same for the same normalized value of the impedance and admittance. So, as we looked at the point last time, which were some special points on the Smith chart, let us look at these points now for the admittance Smith chart. So, if I take the Smith chart and say, suppose these values are not impedances, but they are admittances. That means, if I replace r by g and x by b, this point represents g equal to 0, b equal to 0, which is open circuit. This point represents g equal to infinity, b equal to infinity, which is short circuit. The upper half, which represent positive value of susceptance, that represent capacitive loads, and the negative value of susceptance represent the inductive load. So, if I keep the Smith chart fixed, then while doing calculation with the admittances, the upper half of the Smith chart represents the capacitive load, the lower half represents the inductive load. This is open circuit point and this is short circuit point. Since the resistance circles are symmetric, there is no difference. So, replacing R by G essentially tells you now the G value is increasing from 0 to infinity as we move on this side, but the point is going from the open circuit to the short circuit. Keeping this thing in mind, then the use of Smith chart for impedance and admittance calculation is very straightforward. So, what we will do with this understanding now, we will try to make use of the Smith chart for solving the transmission line problems. The simplest problem one can think of for a transmission line is, for a given load, find the reflection coefficient at the load point. So, now what we do, we discuss use of Smith chart for transmission line calculations. The simplest problem one can solve by Smith chart is, if somebody gives you the load impedance and asks you what is the reflection coefficient. Analytically, I can use the formula ZL minus Z0 divided by ZL plus Z0, but by using Smith chart we will see the problem is much simpler. Remember, the impedances and admittances which we have on the Smith chart are all normalized quantities. So, the first step in any calculation using Smith chart is normalize all the impedances with respect to the characteristic impedances, or normalize all the admittances with respect to the characteristic admittances. So, let us say my impedance was ZL. So, the first step which I do is normalize it to get ZL upon Z0, which is Z bar. Now, read on the Smith chart this point. If you recall, the Smith chart has set of circles now. This is the constant resistance circles which are going like that, or constant reactance circle which go like that. Let us say this is given by R plus Jx, some value. First, identify a constant resistance circle which is having this value R. Let us say that circle is this circle, for which the resistance value is this value R. Then identify a circle for which the reactance value is this X, which will be, let us say, this value. The intersection of these two circles, the constant resistance circle which is having value R and a constant reactance circle which is having value X, this point now represents this normalized impedance Z. So, this point here is that point. Once this point is marked on the Smith chart, then calculation of reflection coefficient is very straightforward, because now the point has been marked on the complex gamma plane. So, if I read off this value on the complex gamma plane, that directly gives you the complex reflection coefficient. So, if I measure the distance from the center from the Smith chart, this is my origin, and let me draw now the complex gamma axis which is not drawn on the Smith chart. So, this is my u axis, this is my JV axis, and this is the origin. If I measure the distance of this point. That gives me the magnitude of the reflection coefficient gamma L. And the angle, conventionally the way we measure the angle on the complex plane, from the real axis, this angle is the angle of the complex reflection coefficient at the load end. So, this angle is nothing but theta L, and this distance is mod gamma L. So, this one is mod gamma L. So, first thing, on the standard Smith chart, you find out the radius of this by using any scale, then measure this distance. The maximum distance on the Smith chart is unity. So, any distance which you get on the Smith chart, normalize with respect to the maximum distance, that quantity directly will give you the magnitude of the reflection coefficient. And the angle which this radius vector makes with the right hand horizontal axis, which is the real gamma axis, that is the angle of the reflection coefficient at the load end. So, without doing any calculation, just by measuring this distance and this angle, I can get the reflection coefficient from the complex impedance. Exactly same thing I can do for calculating the reflection coefficient from complex admittance also. So, instead of impedance, if I had admittance for calculation, then my normalized value of admittance is G plus JB. Now, in this case, as we mentioned earlier, we keep the Smith chart same. So, let us say this circle which we have here corresponding to this is the value which is this G value, and a circle which passes through this, let us say this value is the B value. So, this is this G value, this is the circle which is the susceptance value. So, this is the point which is y bar. However, now if I want to find out the complex reflection coefficient, remember now the real u axis or real complex real reflection coefficient axis is not on the right, because we have kept the Smith chart fixed, and for admittances the coordinate axis has been rotated by 180 degrees. So, for admittances the real u axis is this axis, and the imaginary gamma axis is JV axis. So, for this point here, which is the admittance point, I have to measure the angle from this axis now. So, this distance from center to this point, that gives you complex reflection coefficient magnitude. So, this is mod gamma L, and the angle of reflection coefficient is measured from this axis. So, this angle is angle theta L. So, keeping in mind whether we are using normalized impedances or normalized admittances, appropriate rotation of the coordinate axis has to be made on the Smith chart. But once you do that, then the calculation of the complex reflection coefficient is very straightforward. Mark the normalized point on the Smith chart, find out the radial distance from the center of the Smith chart to that marked point, that gives you magnitude of reflection coefficient. Measure the angle from the real axis of the reflection coefficient for the radius vector, and that gives you the angle of the complex reflection coefficient. One can have exactly opposite problems. Many times somebody might give you a reflection coefficient and you have to find out what is the corresponding load. So, problem is very straightforward. Mark the point on the complex reflection coefficient, the magnitude is given to you, the angle is given. So, you can draw this point. Once you get this point, read off the circles which are passing through these points. So, essentially you read off the coordinates on this constant resistance and constant reactance circle and that gives you the corresponding value of the impedance. So, without doing any analytical calculation, just by graphical measurements of angle and distance, you can find out the reflection coefficient from the impedance or admittance and vice versa. One can now go to the next stage, that if the load impedance is given to you, you would like to find out the reflection coefficient or impedance at some other location on the transmission line. So, the problem is given ZL, say normalize, or YL, and you want to find Z at a distance L from the load. Go to the Smith chart. Generally, we, just for the clarity to represent the Smith chart, we draw only these 3 circles, R equal to 1 circle, R equal to 0 circle, then the reactance circles, which are just 2 circles like that, this line. So, this corresponds to x equal to plus 1, x equal to minus 1, R equal to 1, and R equal to 0, x equal to 0. Nice. So, normally, just for clarity, we just draw only these few circles to represent the Smith chart. Now, the first step involved that you have given the normalized impedance. If the impedance was not normalized, we normalize it first. Mark this impedance on the Smith chart as we did in the previous case. So, find out the constant resistance and constant reactance circles corresponding to this load. The intersection point of these 2 circles will represent the load, which is ZL prime. So, this point is ZL prime. So, that corresponds to this circle passing through this, a circle which is a reactance circle passing through that. So, this is my load point. Now, as we have seen earlier, when we move on the transmission line, the magnitude of reflection coefficient remains same and the point moves on a circle, keeping that magnitude constant. That means, as we move on transmission line, the point moves on the constant VSWR circle passing through this load. So, now what we do, once this point is marked, we take compass and draw a circle passing through this point, which is a constant VSWR circle. Okay. Now, as we move on transmission line, the angle changes by 2 beta L in the clockwise direction. Normally, for the standard Smith chart, instead of marking the angles on the periphery, the distance is directly marked on the periphery of the Smith chart. How do we do that? A distance of 2 beta L, if I take one rotation on the Smith chart, the angle change will be equal to 2 pi. If I move on the Smith chart by 2 pi, that is equal to 2 beta L equal to 2 into 2 pi by lambda into L. So, L will be equal to lambda by 2. That means, one full rotation on the Smith chart or the constant VSWR circle corresponds to a distance of lambda by 2. That means, if I move by a distance of lambda by 2 on the constant VSWR circle, I reach to the same point. And that makes sense, because if you recall the characteristic of transmission line, we had seen that the impedance characteristic of transmission line repeat itself for every distance of lambda by 2. That is what essentially we are reaffirming, saying that by taking one rotation on the constant VSWR circle, we reach to the same point, and beyond that again the characteristics are repeated. So, the angles here now, which are the load angle minus 2 beta L now can be calibrated directly in terms of the wavelength. So, generally we have the outer circle of the Smith chart marked with the wavelengths and with a calibration that the full one rotation on the Smith chart is equal to lambda by 2. So, the distance from this point to this point is lambda by 4, from this point to this point is lambda by 4. Once we get that, then now I want to find the impedance at a distance L, this impedance we want to find out. So, now you move from the load impedance by a distance L or rotate this point in the clockwise direction by an angle which is equal to 2 beta L. So, let us say this was the initial angle which was there. I rotate now my point on the constant VSWR circle by an angle which is 2 beta L. Keep in mind, we are rotating in the clockwise direction because we are moving from the load towards the generator, and distances measured towards the generator are positive distances. That means the L is positive and therefore the angle becomes more negative. So, the point moves in the clockwise direction. This sense of rotation is very important in doing all transmission line calculations. So, if I move in the clockwise direction by a distance of 2 beta L, I would reach to the location L on the transmission line. So, this point then, this point here would correspond to the reflection coefficient at a distance L from the load. The magnitude of reflection coefficient remains same, which is same as this. So, this angle was theta L. This angle now will be the angle of the reflection coefficient at location L. I can read this angle, the magnitude is same as what I had got from here. So, I got the complex reflection coefficient at location L. So, if this is my transmission line, this is my load impedance ZL, the reflection coefficient here was gamma L. If I move a distance L from here, the reflection coefficient at this gamma is represented by this point. Once I get the reflection coefficient at this, now I can just find out what are the constant resistance and constant reactance circle are passing through this point, and I can read off that value. So, I can get the impedance corresponding to this point, which is nothing but the transform impedance at a distance L from the load. So, this point represents gamma at a distance L, and if I read off the value of the impedance, that will be the impedance at that point at a distance L. So, this here, this is the impedance Z, which we will see at this point. Analytically, if you remember, the impedance transformation requires calculation of the cosine, sine functions, and the expression is rather complicated. With the help of Smith chart, the impedance transformation is very simple. You simply draw this constant VSWR circle passing through the load point, move by an angle which is equal to 2 beta L, read off the value of this new point which you have got here, that gives you the transform impedance at a distance L. So, the calculation of impedance and reflection coefficient at any location, other location on the transmission line, is extremely simple and straightforward by using the Smith chart. Now, in this case, we were transforming the impedance which was load impedance to a location L towards the generator. One may have a general situation that the impedance is given at any arbitrary location on transmission line, and you would like to find the transform impedance at some other location on the line. How does the procedure changes? The procedure is exactly same. Wherever you know the impedance, first mark that impedance, draw the constant VSWR circle passing through this point, move by an angle 2 beta L, either clockwise direction or anti-clockwise direction, depending upon whether I am moving towards generator or away from the generator. Find the new point, read out the value, that will give you the transform impedance at the new location. So, in general case, either I might move in the clockwise direction or I might move in the anti-clockwise direction, and that will depend upon whether I am moving towards the generator or away from the generator. So, let me again mention that the sense of rotation in impedance transformation calculation is extremely important, because that tells you whether you are moving towards the generator or away from the generator. So, in all transmission line calculations, you should always remember which direction the generator is, because that will decide the movement on the transmission line, and that will decide which way you should rotate on the constant VSWR circle on the Smith chart. If I replace now the impedances by the admittances, if I am not interested in the calculation of the reflection coefficient, if I am interested only in the transform admittances, then the axis for the reflection coefficient do not come into picture. So, the procedure for transforming the impedance and the admittance are exactly identical. What do? You simply take this point as a normalized admittance point, mark the normalized admittance there, draw this circle which is the constant VSWR circle, rotate it by an angle which is equal to 2 beta L, read this point will now correspond to the admittance at that location, and that value can be straight away read off from the Smith chart. So, the transformation of impedance or admittance is exactly identical on the Smith chart. Only, as we saw earlier, if I have to find out the phase of the reflection coefficient, then only marking of the reflection coefficient axis comes into picture, and then you have to remember that for the impedances real axis is rightwards, whereas for the admittances the real axis is leftward. But otherwise, for impedance transformation calculations, once the impedance and admittance is normalized, the procedure for the transformation is exactly identical. Next thing then one can ask is that, well, I have this load impedance which is connected to the line. The parameter which is of interest is, one is magnitude of reflection coefficient, which tells you the reflection, but we have defined another quantity which is a measure of reflection, and that is the VSWR. So, one way of finding VSWR is you get the measurement of the reflection coefficient, magnitude of reflection coefficient from the constant VSWR circle, then use the formula 1 plus mod gamma L divided by 1 minus mod gamma L, and you will get the reflection coefficient. However, once you have a Smith chart with you, you do not have to do even this calculation. You can just read off the value on the Smith chart. So, again, let us say this is my Smith chart. And let us say I have some impedance which is marked here. This is my some load impedance ZL. As routine, we draw the constant VSWR circle passing through this. So, we get a circle which is this. Now, as I move on the transmission line, I move on this circle. Okay. Now, recall the VSWR is nothing but ratio of the maximum impedance seen on the line divided by the characteristic impedance. We had derived it earlier. So, we have R max which you see on the line, which is equal to Z0 into the VSWR, or in terms of normalized quantity, if I take R max normalized, that is R max divided by Z naught, that is nothing but is equal to rho. So, the maximum value of the resistance in terms of normalized quantity, that is nothing but the VSWR. Now, as we move on this circle here, the highest value of resistance will be seen when this circle intersects this line. So, the rightmost point on this circle corresponds to an impedance which is R max normalized, and the reactance for that is 0. So, this point here, the rightmost point on this axis, that corresponds to normalized R max, and normalized R max is nothing but rho. So, if I read off the value of this point from the Smith chart, this straight away gives you the VSWR. So, this quantity straight away gives me the value of rho. Similarly, as we know, the minimum value which we see on transmission line is Z0 divided by rho. So, we have seen earlier R min is Z0 divided by rho. So, again normalize R min will be 1 upon rho. So, on this circle, the minimum resistance which I see corresponds to this point. So, this value here, if I read off, this value will directly give me 1 upon rho. So, again, once the load impedance or any impedance is marked on the Smith chart, and this circle, which is called the constant VSWR circle, is drawn on the Smith chart, then calculation of VSWR, reflection coefficient, transformation impedance is a very straightforward problem. It is just a matter of reading of the values from different locations on the Smith chart. So, this is the way you can calculate VSWR using Smith chart. Okay. Next thing one can do is find out the location of the voltage or current maximum or minimum on the transmission line, and then one can use that information to find out, just looking at the standing wave pattern on the transmission line, what kind of load the transmission line is terminated in. So, let us say, again take a simple case. Let us say there is some load impedance. You mark that load impedance on the Smith chart, and you want to find out what is the distance of the voltage maximum or current maximum or voltage minimum or current minimum from the load end of the transmission line. So, as we did earlier, so what we want to do now is you want to find distance of voltage or current maximum on the line. Let us do the same thing. We take the Smith chart. Mark the load impedance on the line. Let us say the load impedance is somewhere here, the point. This is nothing but your ZL normalized. Again, first step, draw the constant VSWR cycle passing through this point. So, I get through this point. Now, if you go back to your basic understanding of transmission line, we know that at the voltage maximum the current is minimum. So, at that location the impedance seen is the maximum impedance, which is nothing but R max, and wherever you have voltage minimum, at that location the current is maximum and the impedance seen will be R minimum. That means the extreme point, which is this point, this point corresponds to an impedance which is R max. That means, this corresponds to a location on transmission line where voltage is maximum or current is minimum. So, this point here now corresponds to the voltage maximum or current minimum point, minimum location. Similarly, this point here, which represents the minimum resistance on the line, corresponds to voltage minimum or current maximum location. Okay. We want to find out this location from the load. Job is very simple. You draw a radius vector passing through the load here. If I now move towards the generator up to this point on the constant VSWR circle, I will reach to the location where the resistance is maximum or the voltage is maximum. So, essentially find out what is this angle, this arc here now. This arc, whatever angle I get, that if I divide by 2 beta, I will get a distance of the voltage maximum from the load point. I can use our understanding that the minima voltage minima and voltage maxima are separated by a distance of lambda by 4. So, I can add a distance of lambda by 4 to find out the location of voltage minimum once I know this distance, or I can measure this angle all the way up to this divided by 2 beta to find out the location of the voltage maximum. So, if this angle was theta max, then the location of voltage maximum, this L max will be equal to your theta max divided by 2 beta. So, finding the location of voltage maximum or current minimum is extremely straightforward. Once you mark the impedance on this, draw the constant VSWR circle, just find out the angle from this radius vector up to this horizontal line on the right hand side, and you will get this angle, which if you divide by 2 beta, you will get the distance of the voltage maximum. We will continue with this, and then in the next lecture we will use this information to find out what is the impedance just by looking at the standing wave patterns on the transmission line.